Hi there! As promised, today we'll talk about the latest and last unit of the Theremin V.2, the audio low-pass filter, which will be responsible to remove most of the harmonics from the Theremin audio output, leaving mostly the fundamental sine wave. This profoundly changes the timbre of the sound. Inserting or removing the filter from the audio path of the Theremin allows us to change its timbre from one that is warmer to one that is fuller. You can compare a sound made mostly of the fundamental frequency as the one of a flute, while the one with the whole harmonics in it most similar to the one of a violin. Let's see how this is done. The schematic is very simple, and we have seen already something similar in other videos. The core of this filter is the op-amp NE5534P, which we have used extensively in other Theremin units. The op-amp makes this filter an active one, and this particular configuration is called silent key, from the name of the two engineers that invented it. It is a third-order low-pass filter obtained by putting in series a passive first-order low-pass filter made of R1 and C3, and an inactive second-order filter made of R2, R3, C5 and C4. The calculation of the components of this filter are relatively complex, so when we design such filters we start from defining certain parameters that highlight certain aspects of the filter with respect to others. Without going too much into the details, I just say that I made the calculation based on the Butterworth filter, a design that sets those parameters we just talked about in such a way to provide the most possible flat band in the passband region, while assuring a smooth transition from the passband to the stop band. The passband region is the region of the response curve of the filter where the signal is supposed to pass through unaltered. In the stop band region instead, which is the band where the filter actually modifies the input signal, the response curve goes down fast with the increase of the frequency. And in fact, this particular filter has the capability of reducing the input signal of 60 dB per decade, or 18 dB per octave, as we can observe by the response curve of the filter in the schematic. The cutoff frequency of this filter is 5 kHz, which is the frequency where the attenuation falls below -3 dB, about here in the diagram. If we look for the attenuation of 10 times 5 kHz or 50 kHz, we find this point which corresponds to -60 dB. Because of the characteristic of its response, this filter seems to me very appropriate to cut the most part of the harmonics from the Theremin sound, leaving unaltered the signal at the fundamental frequency. I chose the 5 kHz cutoff frequency because the band at which the Theremin works has the upper side just below the 5 kHz threshold, so the filter will not attenuate the fundamentals that we need, but will attenuate everything else. Here is a circuit I built on a breadboard. You may have noticed the little device that I presented in the previous video to provide a dual power supply to the breadboard. I have already connected the oscilloscope probe to the output of the low-pass filter, and I also connected the noise generator that I presented some time ago to the input, setting it to produce white noise. The noise generator will provide a signal with frequencies spread all over the spectrum. The filter will take away all those frequencies higher than 5 kHz according to its response curve. Connecting the output to the oscilloscope, and in particular to its spectrum analyzer functionality, we will be able to visualize the response curve of the filter and see if it behaves like we expect. So now, let's turn on the noise generator, and here is the response curve of the analyzer. Now, knowing the amount of dB per division on the vertical axis and the frequency at the center of the display, we should be able to evaluate the cutoff frequency. Remember that the cutoff frequency is measured when the output signal goes 3 dB below the value within the passband region. So, if we now shift the image to the right until the center vertical line hits the 3 dB attenuation point, we can read on the horizontal axis the actual cutoff frequency, which seems about right around the 5 kHz we expected. And that proves that the filter does the job for which it was designed. Let's now run a test along with all the other Theremin units. I have connected the audio low-pass filter in between the volume control unit and the audio amplifier. This way the Theremin audio signal will be filtered before being amplified, so that it will take out the majority of the harmonics from the sound and leave only the fundamental sine wave. In the final assembly, I will add a switch to insert and remove at will the filter from the sound path. This way, I will be able to have a Theremin sound with two different timbres, a basic and warm timbre, and a composite and fuller timbre, depending on the kind of music or effects that I want to obtain. Let's now make some noise to see what the new sound looks like. As a way of comparison, here is what the sound is like without the filter. Note the difference in fullness and warmness between the two. Personally, I like more the filtered sound, but sometimes it is more appropriate to use the one without the filter. This was the last unit that I decided to add to the Theremin. It is always possible to make additional units to generate more timbres or to obtain other kind of effects like reverberation, echo and different kind of distortions. But I had to put somewhere a boundary on where to add something else to the Theremin, and I think this is the one. In any case, other audio features can be still obtained with external devices added in between an instrument and an external amplifier. The possibilities are in fact endless. What is left now is to wait for the PCB I ordered to build the final version of the audio low-pass filter, test the circuit in its final version, and then start working on the cabinet that will host all the circuitry and make the Theremin more professional looking. All of this not necessarily in this exact order. But before closing, I would like to make an announcement that hopefully will please all the followers of this series. I decided to write a book to collect all the information that I generated in all the months I worked on this project, and more. The book will contain detailed explanations on all the units of the Theremin, in both versions 1 and 2, as well as detailed information for tuning the various pieces and to put them together in a nice, professionally looking box. The book will contain also all the schematics and pointers to the locations of the Gerber files necessary to create the PCBs, or to have them professionally built. I will also add some instructions on how to use the Theremin properly. Please let me know in the comments if there is interest in this book. I would greatly appreciate any input from you, the aficionados that have followed me until now. And in the meantime, enjoy your hobby, stay safe, and happy experiments!